All right, let's get right into it. We're starting with what is probably one of the most famous images in all of physics, Einstein's light clock. It's this incredibly elegant thought experiment that really sits at the very heart of special relativity. It's a simple idea, but one with consequences that literally changed our entire universe. So here's the classic setup, right? You've got a box that's moving, and inside, a little photon of light is just bouncing straight up and down between two mirrors. Tick-tock. It's a perfect clock. But for someone standing on the outside, watching this box fly by, the light doesn't just go up and down. No, from their point of view, it traces a longer, diagonal path. Now here's the kicker. The speed of light is the one cosmic speed limit. It's always the same. So if the path is longer, it must take more time. The only possible conclusion, time itself is slowing down inside that moving box. And that right there is time dilation, the absolute bedrock of modern physics.
It's brilliant. It's revolutionary. But what if it's not the whole story? The source material we're digging into today asks a really radical question. What if this beautiful, simple experiment completely forgot about the most important character in the whole drama? The observer themselves.
And this gets us to the absolute core of the critique, this idea of the forgotten camera eye. This isn't just about someone watching, It's about how they watch and the actual physics of perception.
This slide really lays out the two competing ideas. On one side, you have the God's eye view, which is what classical physics, and Einstein's thought experiments, tend to use. It's this abstract, all-seeing perspective that sees the entire system, all at once in a single instant. But on the other side, you've got the camera eye. That's us. That's a physical observer, a single point in space that has to actually wait for light to travel across space and hit a sensor, like your retina. This observer doesn't just see now, they have to actively piece together an image of reality from old, delayed light signal.
So, and this is the crucial point, the world you think you're seeing in this very moment is, well, it's kind of an illusion. The sources use this incredible Japanese word, damashie, which means a deceptive picture, an optical illusion. Your reality is a collage, an intricate picture assembled from bits of information, light rays that all left their sources at different times in the past. Okay, let's walk through exactly how your brain pulls this off. Just think about it for a second. For light from something far away and light from something up close to reach your eye at the same time, the light from farther away had to have left earlier. So you have this flood of signals, all from different moments in the past, all arriving at your camera eye in a single instant. And then your brain does something miraculous. It takes all this delayed, flat data and reconstructs it into the seamless, three-dimensional world that you experience as right now.
So you might be wondering, how could physics possibly have overlooked something that seems so basic? To get that, we have to travel back in time to a huge fork in the road, a moment when science was faced with two experiments that seemed to say completely different things.
So, way back in 1729, you have James Bradley's discovery of stellar aberration. He found that because the Earth is moving, we have to physically tilt our telescopes to catch the light from distant stars. That was a huge clue that an observer's motion actually changes how we perceive the path of light. Fast forward to 1887, and we get the super famous Michelson-Morley experiment. They were trying to find the ether wind, this invisible medium that everyone thought light traveled through, and they found absolutely nothing. That null result is what directly led Einstein to publish his theory of special relativity in 1905.
The critique we're looking at today argues that this moment in history was, and I'm quoting directly from the source material here, a historical buttoning error. Like when you button the top button of your shirt wrong and then every single button after that is just a little bit off, physics made a choice that set it on a very specific path for more than 100 years.
So, here were the two paths physics could have taken. On one side, you have the mainstream path, born from the Michelson-Morley result. There is no absolute frame of reference, no ether, so the speed of light must be the same for everyone, no matter how they're moving. That's the foundation of relativity. But this critique says, what if you combined both experiments? Then, a totally different picture emerges, one where there is an absolute stage for the universe, the electromagnetic field, and that light always travels at an angle inside moving objects, just like Bradley had already shown.
So, in this alternative view, the electromagnetic field is the absolute unmoving stage of the whole universe. Think of it like the invisible grid in a 3D modeling program like Blender. It's just there. It doesn't move. And in this model, the cosmic speed limit, c, is constant relative to this field, not relative to every single person or spaceship zipping through it.
Okay, so now we're going to bring it all together.
We're going to take this idea of the camera eye, the reality of information delay, and this idea of an absolute EM stage, and we're going to go back and look at Einstein's perfect clock one more time. And this is where things get really, really strange.
We have to ask the most important question of all. The light inside that clock is physically bouncing in a straight line, sure, but is a straight line what our camera eye, what a real physical observer would actually see?
It all boils down to this simple logic. For you to see the entire path of that light beam all at once, in a single snapshot, the light from the parts of the path that are farther away from you had to leave earlier than the light from the parts that are closer. That's the only way all those light rays can arrive at your eye at the exact same moment. So the image you see isn't a picture of one instant in time, it's a map built from many, many different departure times.
So how on earth do you draw a map that includes this hidden layer of time information? You know, a normal graph can show you where something is, but it can't show you when the light from that spot had to leave to get to you. Regular geometry just can't do it. To account for this lost dimension of time, this phase delay, you need a more powerful mathematical tool. And that tool is what's known as complex space.
Now, don't let the name complex space throw you off. The sources use this absolutely brilliant analogy to explain it. Imagine a piece of dried wakame seaweed. It's flat, it's brittle, it's two-dimensional. That's kind of like the flat image that hits your retina. All the real-world depth and time information has been squeezed out. But what happens when you put it in water? The water is like that missing time dimension. It's the imaginary axis in complex math. And suddenly, the seaweed expands, it unfurls, and it blossoms back into its full original three-dimensional shape. That's what complex space does. It mathematically adds the water back in to restore the dimension that our perception flattened out.
And here it is. This is the climax of the whole argument. When you take the path of that photon in Einstein's clock, and you plot it on this new kind of map, a map that actually accounts for all the different departure times needed for the light to reach your camera eye at the same instant, the path is no longer a straight line. The very geometry of information arriving at your eye bends what you perceive into an arc.
So, at the end of the day, this leaves us with two profoundly different ways of looking at reality, both trying to explain the same universe. Let's just put them side by side so we can see just how different they are.
Okay, let's break it down. Mainstream physics says space-time itself is flexible. This critique says no, there's an absolute unmoving stage called the EM field. Mainstream physics says the speed of light is constant for everybody. The critique says it's constant only relative to that field. In the standard model, the observer is just an abstract point of view. In this critique, the observer is a physical machine that has to reconstruct reality. And that leads to the biggest difference of all. Is reality some objective state that's out there, or is it your own personal projection built from old information from the past?
And that brings us to the final, massive question that this whole line of thinking leaves us with. Are we all just actors on a single, shared, objective stage that we call reality? Or is the world that each of us is experiencing a deeply personal projection, a unique movie being rendered just for you by your own mind, based entirely on old light, a picture of a past that we all mistake for the present?